So today we're going to start looking at chapter 4. And this chapter is on two different kinds of functions, rational and radical. So rational functions are functions that look like fractions, okay, like that. And then radical functions, those are functions that have roots in them, like square roots or cube roots. That's going to be next week. So this week is functions that look like fractions. So that's what a rational function can look like. The top and the bottom are what we call polynomials. So polynomials, I think we talked about different types. They can be linear, they can be quadratic, they can be cubic. Right? There's all different kinds of polynomials. The only restriction is the bottom polynomial cannot just be the number 0, because technically just a number is a polynomial. We can never have a 0 in the bottom of a fraction. Okay. So that's an example of a polynomial. That's a quadratic in the top. What makes the top a quadratic?
The square root.
The square root, right? It's got an exponent of 2. And the bottom one, that would be linear, because what would the exponent be on the x, even though there's not one written?
Just 1.
It would be a 1. So that's a quadratic over a linear polynomial. Okay. And that, when you put it together, is a rational function. Let's see. There's another one. I'm not going to do anything special with these. I'm just showing you examples. The top one is a polynomial. And what's the highest exponent in the top one for g of x? 2. And that makes it a...
Quadratic.
Yeah, so that's a quadratic in the numerator. And what kind of polynomial is in the denominator? Yeah, another quadratic. So those are examples of rational functions. Polynomial in the top, polynomial in the bottom. Any questions, or anyone want to see like another example? All right. So one thing that we have to be careful about with any fraction is dividing. What do you never want to end up with in the bottom?
0.
Yeah, you never want to end up with a 0. Can anybody tell me for f of x, that means you would not want to plug in what number? Yeah?
3.
3. You wouldn't want to plug in 3. You could plug it in the top and you get 10, but in the bottom you get 0. Can't do that. All right, so anytime we set up a rational function, we've got to make sure that the domain is every number except ones that would cause us to divide by 0. So in that last problem, it would be every number except 3. That's pretty much the only restriction that you have to be careful with. We're not going to really have square roots, because if you put a square root in it, that makes it a radical function. And that's not what we're studying in the first 2 sections. In general, you do have to be careful when you have square roots. We're just not going to have that in this section. All right, so we'll try a couple questions where we see if we can just figure out the domain of this rational function. All right, so what makes it rational is that it's a fraction. And you got a formula in the top, that's a polynomial, and a formula in the bottom. So first I'll ask, what number do you want to avoid here? 3. Now when you write the domain, you generally don't write what you can't use. You write what you can use. So think of a number line. Oops. Sorry. Okay, so think like a number line. Here's 3. Okay, we can't use 3. Could I pick a number higher than 3?
Yes.
Yes, that would be okay. So I could pick something that's higher. Could I pick something lower?
Yes.
That's fine. So basically, the entire number line is shaded, except 3. There's like a hole in the graph right there. So let's see if we can describe. We have 2 different parts, everything below 3 and then everything above 3. Let's see if we can just describe each part. Okay. In the below 3, what's the lowest that interval 1 goes?
Negative infinity.
It just keeps going to negative infinity. Do you ever reach negative infinity? No. What's the highest that interval 1 goes?
Less than 0. Anything less than 2.3.
So it does go right up to 3. Now it's just a question, does it include 3?
No.
No. So it's like 2.99999. All right. Now let's describe interval 2. What's the lowest interval 2 goes?
3.
3. Does it include 3?
No.
No. What's the highest it goes? Goes to infinity. And does anybody remember the symbol that we put between the 2?
U.
Yeah, we put that U. That's how you would write the domain as an interval. Okay, so there's 2 different ways. The first one is a graph. The second one is an interval. I can even do it a third way, as an inequality. I could write x is less than 3, or x is greater than 3. So which one of those answers is right? You're out. It depends if they ask you to graph it, write it as an interval, or write it as an inequality. There's 3 different ways you can write the answer.
Now, quick question.
Yeah.
So, can you write it also like all real numbers and then off to the side like x can equal 3?
Yeah, you could write, I guess if they were looking for like a phrase, like a sentence, then you could write x is all real numbers except 3, like you said. But if they ask specifically for like a graph, an interval, or an inequality, you'd have to write it one of those ways. Yeah. This one didn't really say which way they wanted, so I would accept what you just said because they didn't say you had to do it any of those ways. Let's try this one. Okay, so here's another rational function. We got a polynomial on the top, another polynomial on the bottom. They're both quadratics. And what did I say when we were finding the domain? You just want to make sure that you never do what in this kind of problem?
0.
You never want to divide by 0. So what we need to do is make the bottom a little simpler to figure out. Does anyone remember something you can do with the bottom? What that's called? It involves 2 sets of parentheses. But it helps you to see the numbers that would cause you to divide by 0. Yep.
Factoring.
Right, we have to factor. Factoring is the easiest way to figure out what would cause you to divide by 0. Okay. What would have to be in the first spot in each parenthesis? So when you multiply them together, you get x squared.
X.
Yep, and
X.
and an x. Okay, I think I made a chart in one video at one point. We had like, if your middle was positive and your constant was negative, and I get every possibility. There were 4 of them. But when you have a positive in the middle and a negative at the end, does anyone remember what your signs have to be here? Yeah.
1 negative, 1 positive.
Right, you're going to need 1 negative and 1 positive. And now we need 2 numbers that multiply to give us 2. And I'm going to put the bigger number with the positive because I want the middle to come out positive. So 2 numbers that multiply to give me 2. Yeah?
1 and 2.
1 and 2. And I would do them exactly in that order. Let's check it. X times x is x squared. What's x times 2?
2x.
2x. I'm just going to put that up here for a second. 2x. What's x times negative 1?
Negative x.
And 2x take away 1x gives you
1x.
1x. That's exactly what we wanted. And negative 1 times 2 is negative 2. Perfect. Now the numerator, it doesn't really matter. All right? All we care about is what would cause us to divide by 0. Now, what number would you plug in right there? And if you did, it would make this factor 0. 1. So 1 is a number we have to avoid. And what number would you plug in here that would cause you to divide by 0? Negative 2. So 1 and negative 2 are the two numbers we can't use. Okay. I think it's easier if I show it to you on a graph. Here's 0. There's 1. And here's negative 2. We can't use 1 and we can't use negative 2. So you can pick anything lower than negative 2. You can pick anything in between negative 2 and negative 1. Or you can pick anything bigger than 1. So it's like it's 3 different sections. Let's start with picking anything below negative 2. Anyone think they could tell me how to describe the section that's below negative 2? Call it section 1. Yep.
X is less than negative 2.
Okay. How about as how would you do it as an interval?
Parentheses, negative infinity, comma, 2, parentheses, negative 2 parentheses.
Perfect. So that describes this part. Or can someone tell me how you describe the part between negative 2 and 1? Yeah.
Open parentheses, negative 2, comma, 1, close parentheses.
Perfect. So that describes the middle. And could someone else tell me how you would describe the third interval? Yeah.
Open parentheses is 1, and then open parentheses on infinity.
Infinity. Yeah. So when you have two numbers that you can't use, it kind of breaks the number line up into 3 pieces. We generally won't break it up any more than that. It'll either break up into 3 pieces, or it'll break up into 2 pieces. I forgot where that one went. Was it above it? Oh yeah, right here. 2 pieces. Any question on writing the answer this way? And let's try one more of those. This one's actually a little bit easier than B. It's almost the same problem, but the denominator has already been factored for. Let's do this one as a sentence. Let's write down like X is all numbers except, and then we'll just write down what it is. Anyone think they know the 2 numbers that you can't use for X here? Yeah.
2 and negative 4.
2 and negative 4. Yep. So domain, all real numbers except 2 and negative 4. If it was a multiple choice question, it's just a matter of you being able to figure out how to word it. Because I might word it as a sentence, I might write it as an interval, I might do it as a picture and say which of the following pictures represents the domain. But I could word it kind of any of those ways. Any questions on that? Yeah?
Would it be okay if we did like domain and then we use the symbol for all real numbers, because like that double R, and then we use X can't equal the symbol 2 and 4, negative 4?
Yeah, that's okay. Yep. That'd be fine too. Any questions on A, B, or C? Okay. So, both of these functions that we looked at, I mean, that's kind of complicated. It's got a quadratic and a linear. This one here is a quadratic over a quadratic. So it's not that simple. But the simplest rational function that you can have, and sometimes they call this the parent function, is just 1 over x. That is the simplest rational function you can have. I'm going to graph that on the calculator so we can see what it looks like. Now, before I graph it, can someone tell me what number do you want to make sure you don't use for x in this case?
0.
0. So something weird is going to happen when you get to 0, right? Because you can't use it. So let's graph it, and you'll see what it looks like. Okay, I'm going to do zoom 6. We get a graph that looks like that. Now, just so there's no confusion, that's not quite 100% what it looks like. It doesn't actually stop where it looks like it's stopping. It keeps going up and down on the blue section. What happens is the graph is just getting so steep that the calculator, it can't draw it. So when it starts to get almost vertical, the calculator just kind of gives up. So this part should keep going down, and this part should keep going up, just like that. And of course this part, this did a good job with that goes left and that goes right. That's what a lot of rational functions look like. Now, if you add or subtract a number in the bottom, you can move where that vertical asymptote is. Oh, I shouldn't have said that's what it's called. We'll mention that word in a minute. But you can basically move where this, pretend like there's a dotted line right there. If you put like a +2 in the bottom, now you just change the number. It's not 0 anymore, that would be an issue. It would be -2. So it would move this to the left a little bit. Any questions on what that looks like? Now, as you head further and further and further to the right, what happens to the y value? What does it look like it's getting closer and closer and closer to? Further and further right you go. Yeah, it's getting closer and closer to the x-axis. It actually never reaches it. Right? So if you imagine it like kind of like a bigger picture, it would kind of come down and it would just go like this. And it would just keep getting closer and closer and closer and closer. It would never touch the x-axis. Now, what happens as you head further and further to the left? What does it look like that graph is getting closer and closer to?
The x-axis.
The x-axis again, which would be
0.
0. The difference is the one on the right is kind of coming down towards it and never touching it. And the one on the left is coming up towards it, but never touching it. So in both cases, as x heads to the right, that's what this means. So this is like x goes to the right. Or this means as x goes left, the y value approaches 0. Now, it approaches it, but it never reaches it. And I kind of already said the name for that. But does anybody know the name of a line that like a graph gets closer and closer to, but it never reaches it? It begins with an A. Yeah?
Asymptote?
Yeah, an asymptote. Right? An asymptote is a line that you get close to, but you never reach it. So in this particular graph, y equals 0 is a horizontal asymptote. Now, I can graph that line. I'll put it in as a red line. And let me zoom in. Let me set the y max at like 2. Let me set the y min at 0. And let's see if you can see it. That's not quite what I wanted, but you can get the idea. I actually wanted to do it from 0 to 10. So there's your graph coming down. And then in red, that's the asymptote. So if I make it bigger so you can see it, you can see what's happening. It's coming down, but it's never actually going to touch that red line. It's just going to get closer and closer to it. And that red line was the line y equals 0. Not every rational function is y equals 0, but this one is. So how do you find a horizontal asymptote? Well, you basically look at your graph, and you look at what happens as you keep heading further and further and further and further and further away, either left or right. It's going to be the same thing. As you head further and further and further and further away, ask yourself, what are you getting close to? You're always going to be getting close to something. In this case, it's 0. So to find the horizontal asymptote, look at what happens as you keep going further and further and further and further and further to the right, or further and further and further to the left. For the kind of examples we do, it's usually the same number, no matter which way you head. Okay, so these are all different examples of asymptotes. This one on the left is kind of similar to what we're looking at. It's something that's curving up, and it's getting closer and closer to a dotted line. The one on the right is a little different. It actually does cross the asymptote. But the point of an asymptote isn't what's happening near the origin, because that's very close to the origin. The point of an asymptote is what's happening farther away. All right, so like in this one, it crosses it, comes up, but now it's going to keep getting closer, closer and closer and closer and closer as you head to the right. So both different examples of asymptotes. Specifically, those are horizontal asymptotes. You can have vertical as well. Okay, but we're looking at horizontal. All right, well, let's try this one. It says to find the horizontal asymptotes of, all right, let's plug that one in. 1 over x plus 2. When you type it in, you've got to make sure that the calculator knows you don't want this. That is not the same thing. So what we're going to do is we're going to use parentheses to make sure we get that. We're going to tell the calculator to do 1 over x, and then when it's done that, add 2. Now there's no way the plus 2 is going to end up in the bottom with the x. It's separate. All right, and I'm going to do zoom 6. And then we're going to look at what happens as the graph heads to the left and to the right. We'll do zoom 6, like I said first. All right, let's take that graph. And anyone have an idea where it looks like there might be a horizontal asymptote? Again, we usually draw it as like a dotted line, so I'm going to try to make it the way you'll see it in the book. Yeah?
Y equals 2.
Yeah, looks like there's y equals 0. That's definitely not the horizontal asymptote this time. There's y equals 1. And there's y equals 2, right about there. Now, the pixels, obviously, they make the line kind of thick. So I can't make it any, well, I could make it a little thinner. You can kind of see it's coming down, and it's getting closer and closer to 2 on both sides. So that's your horizontal asymptote, y equals 2. Okay. Find the horizontal asymptote. You do have to know it's y equals 2 and not x equals 2. Okay, x equals 2 would be vertical. Y equals is horizontal. So it basically just ends up in this kind of problem. It just ends up being that number right there. That's the horizontal asymptote. So let's see if we can get that without graphing it in the next one. What do you think the horizontal asymptote would be for this one?
-3.
Yeah, it's y equals -3. Okay, I'll graph it so you can see it. That -3 takes the graph and it shifts it down 3. That's what it does. So let me take that, make it so you can see it. Let's make a line. Okay, and if I put it -1, -2, -3, right about there. Now you can see it's getting closer and closer to -3 on the right and on the left. Yeah, perfect. Yeah. So any questions on why the asymptote for that one is y equals -3? Okay. So again, horizontal. Basically, just look at the number. That's right there. If you ever forget it, just graph it and then just look at the screen, and you can tell by the screen as well. Okay, let's see, we already graphed, I think I just graphed that one, so I'm not going to do that again. All right, let's graph 1 over x. Okay, I'm going to do it again, but this time I'm not going to look at what happens as I head left and right. I want to look at what happens near the origin. So in other words, very small values for x, 0.1 or 0.0001, something like that. So what happens, let me just fix that. Let's put that like that. Like that. What happens as x starts to get smaller and smaller and smaller, like getting closer and closer and closer to 0, but not going negative? What happens to the y value as x gets like smaller and smaller and smaller and smaller and smaller and smaller? Yeah.
The y value shoots up.
Right. All of a sudden, the y value starts to shoot up. So here you're at like 5, 4, 3, 2. It's starting to go up. 1, it goes up. 0.5. Now you're up around here. 0.1. Okay, it might be up around like around there. 0.0001. You'd be up way up there. Okay, it starts to shoot up. And when you say shoot up, what does it shoot up towards?
Positive 50.
Yeah. As x gets closer and closer to 0, from the right side, it shoots up to positive infinity. What about as x gets closer and closer to 0 from the left side?
Negative infinity?
It goes to negative infinity. Yeah, exactly. So when I said as x approaches 0, I said from the right side and from the left side. That's the symbol for the right side. This means as x approaches 0 from the positive side. The positive side is the right side. So as you start getting closer to 0 from the right side, y shoots up to infinity. As you approach 0 from the left side, that's what the bottom one says. As you come at 0 from the left side, your graph all of a sudden goes down to negative infinity. And there's your picture to go with it. Now, when that happens, when you start to approach a number, and all of a sudden one side curves up and the other side curves down, kind of like it just like splits like that, that means you usually have a vertical asymptote. So that we would draw like this. I'm going to make it a different color because if it's black, you can't see it very well. I don't know if you'll see this that way. Let's see. Well, yeah, you can kind of see it. So that, they like to make an asymptote thin because the line is really infinitely thin. But if I make it too thin, you can't really see it. I don't know what color. doesn't really look good with any color. Well, you get the idea. So, vertical asymptote, in this case, goes up and down. What does the vertical asymptote go through? What number?
0.
It goes right through 0. And does anyone remember what letter do you start with when you write the equation of a vertical? With a horizontal, we start with y. Yeah?
Vertical, you start with X.
Vertical, you start with x. Yep. So in this particular graph, x equals 0 is a vertical asymptote. And again, the way you look for a vertical is you look at the picture, and usually as you're getting close to what you think is a vertical, the graph kind of takes off, goes up, and then the other side goes down. Now, another way you can check it if you don't have the graph is plug in a number that's close to the vertical asymptote. Okay, to do this, you have to make it so the calculator lets you type in a number. Right now I can't. It's giving me 0 to 10 and I can't change it. I want to type in my own number. So I'm going to press second, and then I'm going to press window. When you press second window, it brings you into how that table is set up on the screen. I want it to ask me what x value I want to type in. I don't want it to automatically give me one. So set yours up just like that. Independent should be on ask, and dependent, just leave that one on auto. Now, once you have that, press second, and now press graph again. Now when you go to your table, well, at least in mine, there's nothing there because I can now type in what I want. If you already have stuff there, it's going to go to the next spot that's open and just let you type there. Or you can go back up and press delete, and you can delete what somebody else already put in. So let's try the number our vertical asymptote is at. Raina, what number is the vertical asymptote at?
0.
Yeah, it's at 0. Well, what does it say when I try to do the vertical asymptote?
Error.
Yeah, it says error because remember your formula, it's 1 divided by x. What's the only number you're not allowed to use in the bottom there?
0.
0. And I just tried to use it, so the calculator is telling me I can't. What's a number that's really, really close to 0?
0, 0, 0, 1.
Yeah, 0.0001. Look at what you get for y. If you type in that scientific notation, 0.0001, you get 10,000. Okay, so you can tell the graph is going way up. What's another number that's really close to 0, but on the other side? Yep.
It's negative variant.
Yeah, negative 0.001. When you're at negative 0.001, just to the left of that yellow line, you are way down at negative 1,000. That's how you know you have a vertical asymptote. The y value shoots way up and way down. So a lot of times I check it on the table rather than draw a picture. But you can do it either way.
How do you put the table again?
How do you clear it?
Yeah.
Once you go to the table setup like I did earlier, just highlight the number and press delete. But you have to do the table setup first. Now, let's try it. Let's graph another. Let's do x squared plus 3x plus 2. And let's divide that by x plus 1. Now, there is a number here that you can't use. What is the number you can't use?
Negative.
Negative 1. Just because you can't use the number it does not guarantee that it's a vertical asymptote. In the last one it was. Let's graph this. Let's type in x squared plus 3x plus 2 in parentheses, and then divide by x plus 1. So everybody agrees negative 1 cannot be plugged in, right? Okay. So let's go to table, and let's type in negative 1, and it says error, just like it did last time. But let's graph it and watch what happens at negative 1. Does it look like anything happened? No. It almost looks like it's a straight line. So negative 1 is still a value you cannot plug in, but it's not a vertical asymptote. So I might ask you, is negative 1 a vertical asymptote in this problem? And you'd say no. I'm going to show you why. Yeah?
Is it a hole?
It's a hole. Yep, it's a very small hole in the graph. And I can make it a vertical asymptote by just messing that number up in the top a little bit. If I make that 2 or 3, it's not going to be a hole anymore. It's going to be really clear that it's a vertical asymptote at negative 1. There's your vertical asymptote. So why does it show it like that when it's a 3? But show it like that when it's a 2. Right? Just barely changing it, but it looks totally different. Let's look at the top. We talked about this a little earlier. What can you do with something that looks like this to make it easier to kind of look at, easier to work with? Yeah?
Factor.
You can factor. And does anybody know how the top would factor? Yeah?
X plus 1, x plus 2.
X plus 1, x plus 2. Here is the reason why you got a hole in the graph. Because when you factor the top, it has something that's also in the bottom. That's what causes a hole. So if the numerator and denominator do not have any common factors, then you will get vertical asymptotes when the denominator is 0. If the numerator and denominator do have common factor, you will not get a vertical asymptote. You will get a hole in the graph. Yeah. Yep. That's how you find vertical asymptotes. It's the value that makes the denominator 0 as long as you do not have common factors in the top and the bottom. So now if we look at 4a, do the top and the bottom have a common factor of x minus 2 or not? What do you think? Is it?
No.
No. The top is just a number. There's nothing you can even factor in the top. It's not like it's a quadratic. Okay? It's just a 1. So in that case, whatever number would make the denominator 0 is the vertical asymptote. So, yeah.
So what would the answer be to that one?
What's that?
What would the answer be to that bottom right one?
So if I asked you, what are the vertical asymptotes in this graph, you would say none. There are none. In this one, though, there will be none, because there's no common factor. What value would make the denominator 0 in this case?
2.
Yep, 2. And how would you write that as an equation? Because it's vertical. You would put we got to write the equation of the vertical asymptote. Yep.
X equals 2.
X equals 2. Yep. Now what if I gave you this one? X minus 2 divided by X minus 2. First question, can you plug 2 in? No. If you plug 2 in, you're going to divide by 0. So same problem. You can't plug in the number 2. But do the numerator and denominator have a common factor? Yeah, now they do. So if you were to graph this, there'd be a hole in the graph at 2. There would be no vertical asymptote in that problem. Okay, I think I had one more. Let's try this one. Okay, what would be the vertical asymptote in this one? We're looking for the number that would make the bottom 0. Yep.
X equals -3.
X equals -3. Now, what if I change the problem to, what if I did this? What would be the vertical asymptote now?
X equals -3.
It's still X equals -3. This number is what controls the vertical asymptote. This number controls the horizontal asymptote. So each number does something separate. Any question on 4A and 4B, why those have vertical asymptotes? Okay, there's not really a lot here. Just look at something. Okay, we kind of, I guess I can graph that one if you want to see it. When you graph it, make sure you put it in parentheses. So 1 divided by X minus 2. If you don't, it's not going to do order of operations in the way that you want. And because we put that -2, it's going to shift it to the right. And there is your vertical asymptote. It's right at 2. X equals 2. Right. Anyone need me to graph? That was that one, this bottom one. Pretty much the same thing. You see a vertical asymptote at -3. Okay, so this one says find the horizontal and the vertical asymptotes. Now, the problem with this one is it's not set up quite the way that we want. When we want to describe a rational function, you want it to look something like this. 1 over x or 2 over x, something like that. Let me write out what the different numbers we do, okay, in the different spots. So let's say we had something like this. Actually, I want to use the letters, but I want to put them in the correct order. Let's do x minus a times b plus or minus c. I don't think we're going to have to deal with the fourth transformation in this section, so I'm just going to stick with those letters. What does a do? A would shift your graph left or right. Okay, we talked a little bit about transformations when we did quadratics, but that's what A does. So horizontal, shift, left or right. Now, this one is always backwards. So if I put plus a number in the bottom, which way would plus move the graph? Remember, it's backwards. Plus would move it left. And if you put minus a number in the bottom, it would move it right. Okay. B. Well, B is when you multiply by a number in front. Does anybody remember it was a certain kind of stretch? Like if you have x squared versus 2x squared. Yes, that's a vertical stretch whenever you multiply by a number in front. So vertical stretch by factor of whatever B is. Yes. And C. What do you think? What do you think C would do? Yeah.
Vertical shift.
Yep. So that's your vertical shift up or down. Now this one is not backwards. So plus, which way would that go? Yep. Up. And that means minus would go down. So when we want to describe the transformation, that's the last thing they want us to do, describe. This is what you're going to use. The problem is your equation needs to look like this. It needs to have a number in front, a 1 in the top, x minus the number in the bottom, and then plus or minus a number at the end. This one doesn't look like that at all. So what did we talk about the last section we learned something right before the test. What did we learn how to do in that section? 3.3. It was something kind of like this. Remember looking back, remember what did we learn how to do?
You're talking about quadratic formula.
I don't think we did quadratic formula in section 3.3.
Finding the zeros?
We might have talked a little bit about finding zeros. Something else we talked about in that section.
The quotient and remainder.
Yes, a quotient and a remainder. Find the quotient and remainder. That's what you have to do to this one. The only way to figure out the shift and the stretch is to make this look like that. So we have to divide those two things out and get the quotient and the remainder. Exactly. Yep. So what I'm going to do is let me get a blank page next to that, and let me do that up. So x minus 5 goes on the outside, and 2x minus 13 goes on the inside. Now, it's not a very big division problem. That's not really the point of this section. You're not going to have really big division problems. They're going to be about like that, if you have to do it. This is the first one we've had to do it. Okay. First thing we have to do is divide x into 2x. What do you get when you divide x into 2x? 2. Yeah, you get a 2. Now multiply it back out. What's 2 times x?
2x.
2x. And what's 2 times negative 5? Negative 10. And subtract. What's 2x minus 2x?
0.
0. That's gone. And what's negative 13 minus 10?
33.
So that's really going to become like negative 13 plus 10. Negative 3. And that negative 3 is your what?
Remainder.
Yep, your remainder. Okay, and this is how you write your answer. Quotient plus remainder over your original denominator. It's exactly the way you write any answer when you do long division. And if you do that, we're going to get something that looks a little bit more manageable. Okay, what was my quotient here?
2.
2. What was my remainder?
-3.
It's -3, so I guess technically here I could just do -3 because the 3 is a negative. And what was the original denominator? Okay, so now we're getting to something that looks a little bit more like what we want. Okay. What I want in the top is a 1. So the way we get a 1 in the top is we're just going to take the 3 and we're going to put it in front. Okay, so let's put the 3 in front. So 2 minus, and then you'd have something like this. 3 times 1 over x minus 5. If you multiplied it back out, what's 3 times 1? 3. It'll give you right back what you started with. Okay, so now, let's look at that and see if we can identify our transformations. Let's see what we can do. All right, and then we'll describe the asymptotes. So transformations. First one we look at is the A. What's A in my problem? Yep.
1 divided by x minus 5.
So the A is just what's right there.
5.
Yep. So our A is a 5, and it's a negative. So what's that negative 5 going to do?
Horizontal shift right.
Yep. So we're going to shift right 5. Okay, so that's the first one. Now the second thing is the B. What number is right in front of that fraction?
3.
3. There is a negative with it. We talked about what the negative does. I didn't mention it today. We'll come back to the negative in a second. But what's the 3 going to do?
Vertical stretch.
Yep. So vertical stretch by factor of 3. Now, there's a negative. Does anyone remember what a negative does? It causes your graph to do something, yeah?
Reflect over the x-axis.
Exactly. This is a reflection over the x-axis because the b is a negative. Okay, so whenever this number is a negative, it's a reflect over x-axis. Now, you might look at it and be like, wait a minute, where's C? Well, you could think of it this way, or if it's confusing because you're not sure where C is, think of it this way. That's exactly the same thing. Okay, there's a +2 at the beginning. I usually like to put the +2 on the end. But wherever you see the added or subtracted number, that's your C. So what's my C in this case? 2. And that's going to shift it which way?
Up.
Yeah, up. Okay, that's a little tricky to figure out what we just did.
How did you pull the 3 out? To 2 minus 3, and then times 1 over x minus 5.
How did we...
Yeah, how did you just pull that out?
So this is how you can always write your answer to a long division problem. Just like what I put a box around. Just like that.
Yeah.
So the quotient in this case was 2. So I put that there.
Yeah.
The remainder in this case was -3. So that's where the remainder comes from. And I put the negative in front. And the original denominator was x minus 5.
Yeah, no, but like down there, how you wrote it like 2 minus 3.
You divided 3 out of the fraction.
Oh, we pulled the 3 in front. So anytime, like if you had, let's say you had 8 over x, that's exactly the same thing as 8 times One of
Oh, okay.
those.
You have three.
That's what I
fourths.
thought.
You have
I
three. You have 3/4. You have 1/4 3 times.
Yeah.
So if you want to take that number and put it in front, and the reason why we do it is because usually when there's a vertical stretch, it's in front. You can leave it in top. I'm just not sure if people saw it like that and didn't know that that's a vertical stretch. Okay, so any questions on that long division? Because that's something we did last week, and then getting your steps. Okay, so now the horizontal and the vertical asymptote. You can write them right below it. I'm just going to go back over there because I have them written. Let's start with the vertical. I don't see any common factors in the top and the bottom. I see a 1 in the top. I see an x minus 5 in the bottom. No common factors. So what would let's just start with the letter. Vertical is always what letter?
X.
Yep. So it's going to be an x. Horizontal is always
Y.
y. And let's do the vertical first. Vertical is what number would make the denominator 0? 5. So there's your vertical. And I told you earlier, there's only one number you really need to look at up here that tells you the horizontal. That's the one that shifts it up and down.
2.
2. So your horizontal here is y equals 2. Okay, so any question on that? Okay, we have a minute. I can try to do one more. Not doing everything out, but just doing the long division again, so we can remember how to do it. Let me see what the last question is. Okay, yeah, mixture problem. So we've done mixture problems before. I actually think this is an easier type of mixture problem. Okay, when we did it before, we needed to make, I think it was like 2 equations, but we're not going to have to do that. So in this kind of problem, they're going to tell you you have a mixture. They'll tell you how many ounces are in it, and they'll tell you what percent of something is in the mixture. So if you've got a 50-ounce container, right, of liquid, and I tell you that 35% of that liquid is acid, how could you figure out how much acid is in the 50 ounces? It's the same question as if I said you just took a 50-question test and you got 35% of the questions right. How many questions did you get right? Be the same thing. Yeah.
I'd probably double the ounces of the questions in the other one to get 100, and then I know that out of that, I'd be doubling the percentage as well, so I'd be getting 70%.
Okay.
With 70 ounces of acid.
Well, there can't be more acid in the solution than we have to start with. We only have 50 ounces.
Well, no, then we're doubling everything. We're just...
So we have 50 ounces of liquid in front of you, and 35% of it is acid. So it has to be less than 50. Because you only have 50 ounces in the container. So how would you figure out how much of it is acid? Yep.
Multiply it by 0.35.
Yeah. You take 50 times 0.35. So that means in the container, it's a little over a third. Okay, 17.5 ounces of the liquid in front of you are acid, and the rest of it, well, maybe it's just water. Question?
Why do you have acid?
What's that?
Why do you have acid?
I don't know.
Yeah,
That's
why
what,
acid?
that's what the book had. Maybe it's like hydrochloric acid or something.
Why not make like water and poison?
They always use acid.
Why not poison at that point? Just water and poison.
So what if I had 50 ounces and I said 50% of it was acid? you'd do 50 times what? 25. And that would mean 25 ounces of the solution is acid. Okay. Any question on that idea? All right, as long as you get that, then the problem is pretty straightforward. So we're going to take kind of the same setup. You've got a container in front of you, has 50 ounces of liquid, 35% of it is acid, and you're going to pour 100% acid into that container. So what we're going to do is we're going to make the solution stronger. So we're going to concentrate it. Find a graph of the new concentration. All right, let me explain what concentration is. In our problem, concentration is the part of the solution that is acid divided by the total. If you divide those two things, that will give you the concentration. So if you had 10 ounces that were acid, and you had a total of 100, 10 divided by 100 would mean it's a 10% solution. Right, so let's see if we can figure out the concentration. So are we starting with some amount of acid already in the solution?
Yes.
We need to figure that out first. So we have 50 ounces, and 35% of it is acid. So how much acid do we already have in the mixture?
17.5.
Right, that's what we figured out above. So we already have 17.5 ounces. That's acid. And we're adding how much acid to it?
X.
Yeah. We're going to add X ounces of 100% acid to our mixture. So we're going to add X ounces. If you add 2 ounces, then you'll have 19.5 ounces of acid. If you add 10, you'll have 27.5. We're going to add some amount. Now we have to divide by the new total. How much solution did we already have to start with, like the total?
50.
We had 50. And how much liquid did we add to it? X. That is your graph for the concentration. Now, what values of X would make sense? Could we have negative values?
No.
No. X is the amount of liquid you're pouring into the container. The lowest you could pour in would be 0. Can't go any lower than 0. All right, so let's type this in. When you type it, make sure you use parentheses around the top and around the bottom. Okay, so for our window, we can't go any lower than 0. What's the maximum amount of acid we could pour in? Well, we're only limited by how much we have. So doesn't say there's a limit. So let's go up to, we add 150 ounces. Now, why is the concentration? But in this case, we're going to get the concentration as a decimal. What do you think the highest concentration you could have is as a decimal? 100%. And what's 100% as a decimal? 1. So the highest the concentration can be is